Mahender Singh. Yep, the next lecture is by Mahender Singh, who will speak about idempotents of Quandle rings and application to knots. Thank you.
Okay, thank you very much for the kind introduction. And let me thank the organizers for giving me this opportunity to talk about some work that we did recently. So the title of my talk is Idempotents of Quandle rings and application to knots. So let us begin. So quandles are actually non-associative objects. So I hope this fits into the theme of the program. So let's begin with something that has been talked about in this program today by Cindy Sang. So what is a quantum Yang-Baxter equation? So let me be a vector space over a field, and you take the two-fold tensor product. Okay. Then a linear map from V tensor V to V tensor V. Okay. We say it's a linear solution to the quantum Yang-Baxter equation if it satisfies this identity. So here Rij means it acts as R on the ith and jth factor and identity on the third factor. So this is an equality of operators on the three-fold tensor product. Okay. So a solution, any linear operator satisfying this is called a solution to the quantum Yang-Baxter equation. And this equation first appeared in the physics in the work of Yang in 1967 and that of Baxter in 1972. But it is worth noting that this equation had appeared in earlier works in different forms, for example, in the form of star triangle relation and triangle equation, and possibly some other forms, and the experts may know better. Okay, so there is obviously a trivial solution. You just flip the two coordinates. So the map T from V tensor V to V tensor V, which is given by little v tensor little v go to W tensor V, is clearly a solution. All right. Now, using this, let us call it a twisting operator. Using this twisting, we transform this equation into something that a mathematician is familiar with, namely the braid equation. So look at this map. So suppose you have a linear map R from V tensor V to V tensor V. Okay, it's a solution to the quantum Yang-Baxter equation. So this is my quantum Yang-Baxter equation. If and only if this new map, which S is R composed with T, satisfies this equation, which is S12, S12 composed with S23 composed with S12 is same as S23 composed with S12 composed with S23. Here Sij simply means, again, S is it's acting as Ij, as S on the ijth coordinate and as identity on the third coordinate. Okay, and if you just replace this Sij, S12, for example, by an alphabet A and S23 by an alphabet B, then this is simply the braid relation ABA is BAB. ABA is BAB. This is the famous braid relation, and this is one of the defining relation in the Artin braid group. So this is the connection to mathematics that I see. So in order to classify all set theoretical solution to the quantum Yang-Baxter equation, Drinfeld proposed in 1992 that we classify only set theoretical solutions. So what is that? So suppose you have a set and a set map from x times x to x times x, we satisfy the braid relation. Then the pair XRV is called a set theoretical solution to the Yang-Baxter equation. And obviously, by linearizing, considering the vector space over X, we get a linear solution to the Yang-Baxter equation. So Drinfeld proposed that we classify set theoretical solution in order to understand all solutions. And it turns out that a plethora of set theoretical solutions arise from very nice algebraic structures, mostly non-associative. So what we are going to talk about in this work is a class of solutions which actually has another motivation, namely three-dimensional topology, and which are also set theoretical solution to the Yang-Baxter equation. And that is where the Quandles and racks comes into picture. So racks and Quandles are algebraic structures with a binary operation which satisfy axioms which are modeled on the three Reidemeister moves of planar diagrams of knots and links in the 3 space. So I will, for the sake of audience, I will talk about this Reidemeister moves and knots and links in a couple of slides. But before that, let us look at the purely algebraic definition of a rack or a Quandle. So a Quandle is a non-empty set X with a binary operation. Let's denote it by X star Y. And it satisfies 3 axioms. One is the idempotency axiom, namely X star X is X for all X. And invertibility. So right invertibility. That means right multiplication by any element is a bijection of the underlying set. And the third, the most important identity is the right self-distributivity. So you see the identity is X star Y star Z is same as X star Z star Y star Z. So there are 3 defining axioms for a Quandle. One is the idempotency, second is the invertibility, third is the self-distributivity. And what is a rack? A rack is simply the one which consists of second and third. We don't really have idempotency. We need not have idempotency in a rack. Okay? And there are plenty of examples of racks which are not Quandles. We are going to see many examples in the coming slides of Quandles arising in different contexts. So let us observe some properties that comes out of these definitions first. So the second property implies that the invertibility and the self-distributivity of axioms are equivalent to existence of a map Sy from X to X, which is just right multiplication by Y, Sy of X equal to X star Y, being an automorphism, right? Because if you see, look at the third axiom, it says that right multiplication by Z distributes. So it's a morphism with respect to this binary operation. And second property simply says that it's a bijection. In addition, if you have idempotency, it says that it preserves Sy or Y is just Y. It fixes the point. It's a point symmetry. And now connection to the set theoretical solution to the Yang-Baxter equation, racks and Quandles give non-degenerate set theoretical solutions to the Yang-Baxter equation. So non-degenerate means each component map is actually a bijection. And in fact, the solution is given by, suppose X star is a rack, then the solution is given by R of Xy equals to Y comma X star Y. And one can check that this is a bijective and non-degenerate solution. In fact, many other classes of solutions are related to Quandles. So in an earlier talk this morning, we heard about skew braces. So every skew brace gives rise to what you call a biquandle. And biquandles actually arise from underlying quandle. It's a nice work of Eva Horvath, where she showed that every biquandle arises from what you call a biquandle structure on a quandle. So there is a connection with skew braces. Now, before looking at some explicit examples and getting into the main topic, let's see connection with the knot theory. Because these axioms, the 3 defining axioms, idempotency, invertibility, and self-distributivity, are nothing but the 3 Reidemeister moves of diagrams of links. It's a very beautiful connection. So for the sake of readers, I have just incorporated the definition. So what is a knot? A knot is just an embedding of a circle in the 3-dimensional space. And of course, you have one embedding and you have another embedding you would like to talk about when they are equivalent, right? So equivalent here in loose sense is just, if I have 2 knots, I can wiggle one and get the other one. Okay, so in more precise terms, they are ambient isotopic. So we say 2 knots are ambient isotopic if there is a continuous map from R3 times 0, 1 to R3 such that for each t, the map X goes to H of xt is a homeomorphism of the 3 space. The first map is the identity map, and the last map maps the first knot to the second knot. And similarly, a link is just an embedding of a bunch of circles, not necessarily one, but maybe 2, 3, and some finite number of circles. And as I said, you can completely ignore this definition of ambient isotopy. Basically, what simply means that I have two knots suspended in the 3 space. I can wiggle the one and get the other. What I'm not allowed is cutting it and regluing. So just by wiggling, I should be able to obtain one knot from the other. So therefore, now in three-dimensional topology, classification of knots and links is a very important problem because it's also related to classification of 3 manifolds. In fact, every nice 3 manifold can be obtained by some surgery on a knot or a link. So that's the connection with 3 manifolds. So therefore, these are important objects. And we have seen what I mean by equivalence. Loosely, you can obtain one from the other by wiggling it around. Let's see some examples. So one has a trefoil knot. So basically, just take a piece of a string, tie the simplest knot that you can, and glue the ends back. That is what you get is a trefoil knot. Figure 8 knot is like it's a little complicated, but again, you can draw it using a string and placing it in this fashion and gluing the ends. Half link is just you have 2 rings and which are like linked with linking number 1. And this is a famous Borromean rings. These are 3 rings which are entangled. And they have the very nice property that if you just remove any one of them, all 3 of them become untangled. So you can have knots and links on any number of components, and they get more and more complicated if you have more and more crossings. So these are actually the crossings. So what I have shown you on the slide are actually projections of these knots, not really the knots, because knots are 3-dimensional. So as I said, in the preceding slide, what I showed you was projections of knots. So it turns out that it is enough to just study projections of knots, and therefore whole of 3-dimensional study amounts to just studying some 4-valent graphs, which is the combinatorial and from which you can derive some non-associative structures. So let's look at that. So suppose you are given a knot or a link in the 3 space. It's like suspended in the 3 space. You take a projection of that on the plane. Okay, so we say it's a regular projection if the pre-image of every point is at most 2 points. What I don't want is 3 arcs passing through a point. If at all there are 3 arcs passing through a point, you perturb one little bit and move it away from that, right? One can always do, because this is actually ambient isotopy. Because as I said, in loose term, you can obtain 2 links are said to be equivalent if you can wiggle it and obtain one from the other. So every knot or link admits a regular projection. That is not a difficult thing to prove. And once you have a regular projection, but the thing is, when I projected my knot and link on the plane, I lost the information of over and under. Because one arc may be passing over, one may be passing under, and when I project, I lose the information. So I need to incorporate this information on my graph that I have obtained on the plane. Okay, so that I obtain by just drawing one arc as broken, which is under, and the other as complete arc, which is over, just to distinguish which was over, which was under. This is what is called a knot diagram, a very simple-minded object. And it turns out that it is enough to study these diagrams and completely forget about 3-manifold topology. So this genius idea is due to Reidemeister. What he said is, you can just apply 3 kind of moves on the diagrams of knots, and that is enough to tell whether one knot is equivalent to other or one link is equivalent to other. So what are the 3 moves that he proposed? They are the following. So let us look at this. It says that suppose you have a string which is like with a kink, and you, on the other hand, you have a straight string. They are actually the same. Of course, in the 3-dimensional space, they are actually the same, right? But what it means is that on the plane, they are not actually the same as graphs, but we have to declare them as same. So that's the move that we are applying. And the second move, that's called the second Reidemeister move, is if you have one string passing over the other, you can just slide them and straighten them up. That's also an obvious thing in the three space. It's actually an isotopy. And in the plane, as four valent graphs, we are declaring that it is just same as two parallel strings. And the third one is called the third Reidemeister move. If you have three strings, like two crisscrossing like this, and another one on the back or the front, you can slide the third one up and down. Okay, in the plane diagram. So these are the three critical moves that Reidemeister proposed in the 1930s for diagrams of knots. And a very powerful theorem that he proved, although the proof is not difficult, but it has completely transformed three-manifold, three-dimensional topology, is this theorem, proved in 1926 by Kurt Reidemeister. It says that two knots and links are equivalent if and only if all their link diagrams can be deformed into one another by a finite sequence of the three Reidemeister moves that I showed in the preceding diagram, these three moves. These first, second, third, these three moves are enough to check whether two knots are equivalent. So what the idea is, you have two knots and link, project them on the plane, you get the four valent graph and remove the triple points. And now if you can turn one graph into other by applying a finite sequence of these three moves, any combination, you may have like bunch of R1 move, but bunch of R2 move, bunch of R3 move, you apply any sequence. You can, if you can turn one diagram into other in a finite sequence, then the three-dimensional, the knots in the three space are actually the same. They represent the same knot. So the whole three-dimensional topology, three-dimensional study can be now translated completely into planar diagram. And this beautifully translates into algebra in the form of what called Quandles. So here is a connection of Quandles with the Reidemeister moves. It's like one can study these non-associative structures using diagrams. So suppose you have a knot or a link and you projected it on the plane. You give some orientation, some arrows, fix some orientation, okay? And let us call this as a positive crossing, this as a negative crossing. So my rule is the following. My rule is, whenever I have a positive crossing, I label all the arcs by some alphabets. The rule is the over arc act on the incoming arc by the star operation, and we label that outcome, we label the outcome by that arc here. And if it's a negative crossing, we do it by star inverse. What is star inverse? Notice that the Quandle exam says that the right multiplication is invertible, right? So therefore, using that inversion, you can cook up a dual binary operation. Let us call it star inverse. So it's nothing but the S sub X inverse is the symmetry, inverse of the symmetry. And if you, with this convention, if you look at the first Reidemeister move, if you forget about the labeling in this picture, it is just the first Reidemeister move. And if you follow the rule that I just told you, what I get is the over arc X act on the incoming arc, which is also X. I want the outcome arc to be X star X, but it is same as this, but which is same as X. That means X star X is X. So this gives you the first Quandle axiom. Similarly, if you follow the rule that I just told you, you will see that this is same as second Quandle axiom and this is same as third Quandle axiom, because what I want is that this arc should be same as this arc, but this comes out to be labeled by X star Y star Z, and this comes out to be labeled by X star Z star Y star Z. So therefore, the Quandle axioms, which looks completely algebraic object, these axioms are nothing but just algebraic formulation of the three Reidemeister moves of diagrams of knots and links, which is equivalent to classify, which are enough to check whether two knots and links in the three space are same. And since these axioms are just formulation of Reidemeister moves, one expects that one should be able to associate a Quandle to a knot. That's a natural expectation. And in fact, it turns out to be that is the case. So suppose that you are given a oriented knot or link. Given a knot or link, you just put an arrow on any direction you fix. Okay. Then its fundamental Quandle is the following. You take its knot diagram, project it on the plane, you get a four valent graph, and then you label the graph by some alphabets. And the quandle is, you take the quandle which is generated by the arcs of the diagram and put some defining relations. What are those defining relations? Defining relations are exactly what I told in the preceding slide, that whenever you encounter a positive crossing, you say that this Z third arc is same as X star Y. And whenever you encounter a negative crossing, you say that this alphabet W is same as X star inverse Y. So just from the diagram, we can write a presentation for a non-associative gadget that one can associate to a knot or a link in the free space. Okay, and the defining relations are just given by the crossing, the valency 4 vertices on this 4-valent graph that we got in the plane. So for instance, suppose that your link is just bunch of disjoint circles in the free space, 1 circle, 2 circle, and so on, some bunch of circles. Then what is the knot quandle? One can easily see that it is just generated by the arcs, which are just arc number 1, arc number 2, and so on, and relation, but there are no relations here. So it's actually the free quandle of rank n. So this QL is actually same as free quandle of rank n. So just like we have free groups, so we have free quandles, and there is an explicit model for free quandles. And in fact, it comes from free groups. So you take the free group of rank n, and in the free group of rank n, you take the conjugacy classes of generators. And in that, you impose the star relation as conjugation. That gives you a quandle. And in fact, it serves as a model for the free quandle of rank n. And it's a very fundamental and very powerful result of Sergei Matveev and David Joyce, who proved independently in 1982 that this object QL that I just associated to my knot or link is a very strong invariant of my knot and link. So if two knots and links are equivalent, then of course the quandles are isomorphic. But it is almost complete in the sense that if two knot quandles are isomorphic, then the links are either isotopic or isotopic to the negative or the mirror image. It's a very strong invariant. So in fact, for those familiar with knot theory, one can recover many classical invariants of knots and links from quandles. For example, the fundamental group, the Alexander polynomial. In fact, the volume of a hyperbolic knot can be recovered from quandles. So without getting much into topology, let us now get into algebra and see a lot of examples of quandles before we jump into quandle rings. So are there any questions so far? Please let me know. Okay. All right. So let us see some constructions of quandles from various structures. So besides knot theory, quandles arise from various algebraic structures, in fact, various geometric structures, but I will avoid geometric setting. So suppose that you have a group G and an automorphism. Then you define this new binary operation X A star B equal to phi A B inverse. Okay. Phi A B inverse of B. One can easily check that it's actually a quandle structure on G. And in case the group G is abelian and phi is the inversion map, it has a special name called the core quandle. I'm mentioning it because I'm going to come back to it later on. And in fact, further, if G is a cyclic group of order n, this gives you a familiar class of quandles called dihedral quandles, which are often used for coloring knot diagram, and they are actually relatively easy to handle. There is another interesting, another natural construction of a quandle on a group, namely the conjugation, which I just mentioned. So given a group G, you define a new binary operation on the group G, X star Y equal to YX Y inverse. See, notice here that I'm conjugating by Y. So because I want right distributivity, you could have very well defined a left distributive quandle where you would have defined X star Y as X, Y, X inverse. Okay. So just like skew braces, we have left and right, we have quandles left and right. This is called the conjugation quandle of the group G. Let's see another example in another setting. Suppose you have a commutative ring and X a free K module equipped with antisymmetric bilinear form, X cross X to K, let's denote it by this bracket. Then one can define this quandle operation on this, namely X star Y equal to X plus this bilinear form of X and Y times Y. One can check that it's actually a quandle. Further, suppose you have a nilpotent Lie algebra of nilpotency class 3, one can turn this into a quandle by defining this binary operation. X star Y equal to X plus the Lie bracket XY. Okay. In the setting of algebraic varieties, suppose that you are given an algebraic variety and a connected commutative algebraic group, and suppose F from X cross X to A is a regular map, okay, which vanish on these kind of tuples, degenerate tuple XX equal to 0 for all X. Then you can define a quandle structure on this product X cross A, namely XA star YB equal to X plus A plus FXY. So we see that quandles structures arise in various settings. In fact, you can, given any Riemannian symmetric space, so because each point has a local symmetry, so you can define X star Y equal to the symmetry Y acting on X. And one can check that it's actually a quandle structure. Also on surfaces, if you take the set of all simple closed curves on a surface, one can define a quandle structure there also. It's called the Dane quandle. So we see that there are plenty of examples of quandles, and they arise very naturally from groups, from Lie algebras, from algebraic varieties, and so on. What we do is we try to bring a little bit of ring theoretic techniques into study of quandles, because they are non-associative and looks are a very rigid kind of objects. So we try to imitate the construction of what the group ring or the group algebra for quandles. So let us look at the definition. So suppose that X star is a quandle and K is an associative ring with unity. As in group algebra, let Kx be the set of all formal expressions of the form summation alpha x Ex, okay, where E sub x is a unique symbol that I associate to the element little x of my quandle. Okay, so instead of just writing x, I am writing E sub x because sometimes it conflicts. There is a conflict with the operation in the quandle and the operation in this ring that we are going to construct. So just to be on safer side, we denote these generators corresponding to elements of x by E sub x, where alpha x in K and only finitely many of these coefficients are non-zero. Okay, so it's just similar to how we define a group ring or a group algebra. So then this Kx has a free K module structure with basis Ex, and there is a multiplication. Summation alpha x Ex acting on summation beta y Ey, which is summation alpha x times beta y and times E of x star y, where star is the quandle operation. Okay. So this turns Kx into a ring, rather an algebra, which we call the quandle ring or quandle algebra of X with coefficient in K. So this construction we studied with in a joint work with Professor Valery Bardakov, who has a talk later on today, and late Professor IBS Passi. In an attempt to, our aim was to bring model theoretic and representation theoretic techniques into quandle study of quandles, because somehow they are very difficult to handle. So even though the coefficient ring may be associative, which we are taking in this case, it turns out that the quandle rings are highly non-associative objects. In fact, it is always going to be non-associative unless your quandle is a trivial quandle. What is a trivial quandle? Let me recall. Trivial quandle is not like a trivial group, but it can have any number of elements. So X is trivial. X is trivial if X star Y is X for all X and Y in X. So a trivial quandle can have any number of elements. And in fact, they are sometimes quite interesting. Contrast to groups, trivial quandles can be interesting. So just as we have in case of a group ring or a group algebra, the augmentation map, similarly, we have an augmentation map here. We just take epsilon of summation alpha x ex is just sum of the coefficients. One can easily show that it's actually a ring homomorphism, okay? And the kernel is an ideal, what we call the augmentation ideal of this, okay? So in terms of this augmentation ideal, one can give a very nice characterization of when a quandle is trivial. So it's a very simple observation. So we say that it turns out that a quandle X is trivial if and only if the augmentation square becomes 0. It's actually a direct calculation. Okay. So a quandle is trivial if and only if the augmentation square is 0. Recall that the quandle is trivial if x star y is x for all x and y in this. So therefore, this augmentation also has some control on the structure. In fact, there have been some conjecture on the sub-quotients of powers of these augmentation ideals. And I think Muhammad Ilham Dadi has some positive results along these directions. So we are now nearing the main topic that is the title, Idempotents in Quandle rings. Okay. So what are idempotents? So units in groups play a fundamental role in the structure theory of group rings. That's a well-known fact. And in fact, it's a central problem to figure out units in group rings. And there is a whole industry of people on this. What is the basic reason for that? The basic reason is the elements of the group sits inside the group ring as units. So therefore, it's sensible to ask what are the other units? Are those the only units or are there more units? So we ask similar question here, and it turns out that idempotents are the most natural object in quandle rings because each element of the quandle is an idempotent. So therefore, it makes sense to ask what are other idempotents in a quandle algebra or a quandle ring. It's just analogous to groups, but we have to work with idempotent because there are no units here. In fact, it's an elementary exercise that if a quandle ring has a unit, then the quandle must be trivial. One can easily show that. So in contrast, it turns out that idempotents are the most natural objects in quandle rings, since each element is by definition an idempotent of the quandle ring. Remember, because Ex times Ex is what? E of x star x. And by first quandle axiom, it is just Ex. So therefore, each element of the quandle can be viewed as an idempotent in the quandle ring because there is a natural map x goes to Ex, okay, from x to Kx, the quandle ring, right? It's a natural map. And in fact, it's a faithful map because Ex is the set Ex where x is in X is a basis, right? And also we know that computation of idempotents is in general in ring theory is an important problem. It is well known that integral group rings do not have any non-trivial idempotent. It's a result of Donald Passman, I think classical result. In contrast, it turns out that integral quandle rings of many non-trivial idempotent possess non-trivial idempotents. Non-trivial quandles possess non-trivial idempotents. So in the rest of the talk, I will present two results that we proved recently on determining idempotents for certain families of quandles. So to some extent, we determine the idempotents completely. So let us set some definition. So suppose you have a quandle, Kn integral domain with unity. A non-zero element is called an idempotent if U square is U. Okay, so I do not want to include 0. Okay, and let us I of Kx denote the set of all idempotents. And further, elements of the form Ex where x is in X, we call them trivial idempotent because they are trivially idempotent as I have just shown here. Ex times Ex is E of x star x, which is Ex. So they are obviously idempotent. They are called trivial idempotents. What we are interested in is finding what are the non-trivial idempotents. So a non-trivial idempotent is an element of Kx that is not of the form Ex for any x in X. For example, I want an idempotent whether there is something like alpha Ex plus beta Ey, whether there is an element of this form which is an idempotent, and U square equal to U. So we are interested in finding the non-trivial idempotents. Any questions here? So let us see some simple illustrative examples. Suppose you have a finite quandle having a subquandle of order y with more than one element, such that coordinate y is invertible in K. Okay. X is a finite quandle having a subquandle with more than one element. Remember, because if it has one element, I will get only trivial idempotent. So I want it to have more than one element. So that this coordinate is invertible my ground ring. Then look at this element. U equal to summation Ey, where y runs over y, and just normalize it by 1 by order of y. And a direct check shows that U square is identity, is U. It's an easy calculation. Okay. So you do have idempotent, and in fact, it's a non-trivial idempotent because coordinate of y is more than 1. All right. And of course, but in this case, I want this coordinate y to be invertible in K. So I already have some restriction on my coefficient ring K. Notice that we have the augmentation map. And if U is an idempotent, then augmentation value of an idempotent has to be 0 and 1, because epsilon of U square is epsilon of U, right? Which is same as epsilon of U into epsilon of U. So this implies epsilon of U has to be 0 or 1. Okay. So there is some control on the augmentation value of idempotent. And it is a trivial observation that if you take a trivial quandle, then the complete set of idempotent is just a translate of the augmentation ideal. Just a manual check. There is nothing really to explain here. So one can easily check that this set is the set on the right-hand side is an idempotent. If you take any idempotent in the trivial ring, when you square it up, it has to be of this form, because we have this fact that x star y is x for all x and y in X for a trivial quandle. Right? So the more interesting thing happens when you take something non-trivial quandles. And there comes the idea of quandle coverings. So we will need this idea of quandle coverings in order to state our main theorem, where we give a complete characterization of idempotents for a very fairly large class of quandles. So what is a quandle covering? The idea is motivated from topology. We have a covering projection of a topological space. Okay, it has some nice property. In fact, this idea is due to Michael Eiserman, and where he introduces quandle covering and Galois correspondence for quandle covering. So he in fact ended up proving, he defined a fundamental group for a quandle and proved a similar kind of Galois correspondence. So what is a quandle covering here? So suppose that X and Y are two quandles, then a quandle homomorphism is called a quandle covering if it is a surjective map. And for any 2 points, X and X prime in the base space, if you look at their in the same fiber, okay, for any 2 point X and X prime, which are in the fiber of the same point, the right multiplication is the same. Okay, so that means here I have Px. If Px equal to Px prime in Y, then what I want is that right multiplication by X in the quandle X is same as right multiplication by X prime in the quandle X. They have the same symmetry. So quandle covering is a quandle homomorphism. What is a quandle homomorphism? It's just a map which preserves the quandle operation, just like a group homomorphism. In fact, the set of all quandles is a category. Okay, so you have morphisms and so on. And a quandle covering is just a Quandle homomorphism which is surjective with the property that if 2 points in X are mapped to the same point, then the right translation by those 2 points should be the same in the upper space X. There are some, obviously, if you take a Quandle isomorphism, then there will be a unique point, right? So it's obviously a Quandle covering. Some non-trivial examples come from group theory. So a surjective group homomorphism P from G to H yields a Quandle covering from the conjugation Quandle of G to the conjugation Quandle of H, if and only if the kernel P is a central subgroup of G. Remember that if you have a group G, we can turn this into a Quandle called conjugation Quandle, where the binary operation is just conjugation. In fact, it's a functor from the category of groups to the category of Quandles, where G goes to conj. Similarly, if you have a surjective group homomorphism between two groups, it gives you a Quandle covering from the core Quandle of G to the core Quandle of H. What is a core Quandle? Recall core Quandle is just X star Y is 2Y minus X. Okay, it's a special case of the first example that I gave. If and only if kernel P is a central subgroup of G, but in this case of exponent 2. These are very elementary things to check. So therefore, we do have a large supply of Quandle coverings, what we can cook up from surjective group homomorphisms. And another artificial looking thing is the following. Suppose you take a Quandle X, take any non-empty set of your choice and give it the trivial Quandle structure. Every set can be turned into a Quandle by defining X star Y equal to X, right? Then take the product Quandle with the product structure and the projection onto the first factor. XY goes to X. One can easily check that it's a Quandle covering, okay? Because the fiber over each point is going to be the set F, which has a trivial Quandle structure. So all symmetries of all the points are just identity maps, right? So there are plenty of examples of Quandle coverings, and they arise very naturally from group extensions. And what we show is that once you have such a Quandle covering, you have a complete information about the idempotents of the top space if the base space is nice enough. Let us look at the statement. So suppose that P from X to Y is a Quandle covering, and let Fy denote the set of all finite subsets of Y. Take all finite subset of Y. Similarly, for each little y in Y, look at the fiber P inverse of Y. Take the pullback of that. Again, take all 5 finite subsets of this. F of P inverse Y is the set of all finite subset of P inverse Y. And we denote a typical element of this finite subset of P inverse of Y by IY, just for notational convenience. Okay. I have drawn a picture, I guess. Yeah, okay. So let us look at this example. So you have your total space X, base space Y, and a covering P. All right. So for each point Y, if you take the fiber P inverse of Y, okay, it will have a bunch of points depending on how many sheeted the covering is, right? So I take a denote finite subset by that notation. So let's come back to the statement. Let me set one more notation here. Take a basis element E sub X and take another Y element Y, okay, of the space, same Quandle. Then by this bracket E sub Y, I mean this expression. What is this expression? Let's look at it carefully. I'm taking the basis element EX, and then I'm taking the basis element E of X star Y, E of X star Y star Y, and so on, all the way to the order of the symmetry SY, right? Because X star Y is nothing but SY of X, okay? So in other words, you fix an element little y in your X, and take the subgroup SY in the group of automorphisms of the Quandle and consider the SY orbit of the point X. SY orbit of the point X, and take the corresponding generators. So that will be EX, E of X star Y, E of X star Y star Y, and all the way up to order. Okay. And you sum them up. That's an element in the Quandle algebra. Okay. And it turns out that these elements will play a crucial role in determining the idempotents. So we can now state the theorem. It's a joint work with Mohammed Elamdadi, Brendan Nunez, and another student, Dipali. These are based in University of South Florida. So suppose you have a quandle of finite type. What is a finite type? So finite type means each right multiplication by an element is of finite order. So you see, I want here to be a finite order. Okay. So that's the condition I need to impose to make sense of this finite, so that I have the finite summation. So suppose you have a quandle of finite type, and P from X to Y, a non-trivial quandle covering onto some other quandle. And suppose that that other quandle has a property that is quandle ring has only trivial idempotents. So I want the base to have only trivial idempotents. Then the complete set of idempotents of Kx is given by this set. Okay. So this set may look a little complicated, but let me give you a sketch of the proof from the diagram and things will become clear what actually I mean. So we have this, the covering X, the base Y. Okay, so let's observe the following first. Suppose I fix some point Y0 here that I'm fixing here, and take the pullback of that P inverse of Y0. Okay, P inverse of Y0. And consider a finite subset of this P inverse of Y0. So these are the finitely many points that I have drawn: point number 1, point number 2, 3, 4, 5, and 6. Look at these 6 points in the fiber and take their convex combination. So I consider summation of alpha I xi, I from say 1 to 6, and such that summation of alpha I is 1. Okay. One can easily see that this will actually be an idempotent because all these symmetries are actually the same. Now, it turns out that these are not enough. There are something more to be added. So now you take any finite subset J of here J of your set Y. Let's say finite subset is Y1, Y2, Y3, Y4. And for each point, you look at the fiber. So this is the whole fiber, this is the whole fiber, this is the whole fiber, and so on. Okay. Now from each fiber, you fix a point and you take its orbit. That's the orbit I'm talking about here. Similarly, from the other fiber here, you take an orbit, full orbit under the same point whose image is under the same point which lies in the fiber, namely the point x0. And take their sum, but not the convex sum in this case. In this case, the summation of some beta j's or xj's, where summation of beta j's is 0. It turns out that this sum plus this sum actually is an idempotent. And that is what actually this expression is telling. This is the expression. This is the complete, and in fact, to prove the converse, we notice that any element in the quantum ring will be a linear combination of bases. So all these basis elements will lie in some fibers, okay, and we can write it in this form. So that's actually the idea of the proof. So now what can you say about augmentation value of idempotent? So as we observe, augmentation value of any idempotent is 0 and 1. But we did some computational check, and what we figure out is that, of course, one can check that idempotents, one can actually construct examples of quantum rings, let's say over the field of characteristic 2, okay, of mod 2 or the complex quantum rings, let's say of dihedral quantum R3, they can have augmentation value both 0 and 1. One can actually cook up. If I had time, I could have shown you the table. But what actually happened is that instead of that, if you work over integers, there is a strong restriction. And our computations up to quandles of size 7, all the quandles of size 7, we did a magma computation, asserts the following conjecture. Any non-zero idempotent of the integral quandle ring of a quandle has augmentation value 1. We could not find any non-zero idempotent with augmentation value 0 over integers. So it's always turning out to be 1. Of course, over other rings, it can be 0 and 1, as I have already said here. One can easily see small quandles of size 3, but over integers, somehow it is the case. We don't know how to prove it. And also, our computation suggests the following, that the integral quandle ring of a semi-Latin quandle has only trivial idempotents. A semi-Latin means right multiplication is also injected. Left multiplication by an element is injective. So that means y goes to x star y is injective. These are called semi-Latin. Semi-Latin quandles. In particular, if you take a finite quandle, Latin and semi-Latin are the same. So our claim, we believe that all finite Latin quandles, okay, they have only trivial idempotents. Okay. So do I have some time or is?
Yes, we have a few more minutes.
Okay. So I'll just wrap it up. All right. Thank you. So similarly, we give a complete answer to all the idempotents in the quandle ring of what are called free quandles. And the answer is particularly nice in this case. So let me just quickly recall what is the definition of a free quandle. Suppose you have a collection of quandles given in terms of presentation, just like groups. One can do in terms of in the language of universal algebra. Then the free product is defined by this presentation. We add up the generators, disjoint union and disjoint union of relators. In particular, when each quandle is a trivial one element quandle. So there is something interesting here in contrast to groups. What is a free quandle of rank n? Free quandle of rank n is you take singleton quandles, one element quandle, and take their free product. And that's actually your free quandle of rank n. So just have trivial groups, or trivial one element quandle actually. And what we showed is that if you take a free quandle of rank n bigger than or equal to 1, then the integral quandle ring has only trivial idempotents. And the same, in fact, using the same assertion, or in fact, we use a version of the Nielsen-Schaer theorem that you can embed this. Any subquandle will look like a free quandle is free. One can actually show that countably infinite rank free quandle will also have only trivial idempotents. So just a comment about the proof. The key idea is to use the length function on the left normalized expressions of elements of free products of these quandles. And in the last slide, I will not get more into knot theory, but we also give applications of these idempotents to enhance coloring invariants of knots and links. So we can actually cook up. So you take morphisms from quandles to another finite quandle, and instead of that, you consider algebra morphisms. So we are able to, of course, the algebra morphisms is a bigger set. So you take this order tuple, it's a stronger invariant. And in fact, we are able to construct examples of knots where the coloring by the quandle is the same, but when you consider coloring by algebra, it turns out to be different. So therefore, quandle algebra is actually giving a stronger knot invariant than the classical coloring by the quandles. So I think I will stop here. Thank you very much.
Thank you very much. Are there any questions?
We want to ask about zero divisors in group rings. Do you have any ideas? Zero divisors.
Zero. Oh, yeah. Right. So yeah, we have some results about zero divisors with Valery Bardakov. Yeah, but again, we have not really attempted doing it for a large class of large families of quandles, as we are able to do in this case. Yeah, it makes sense. Yes. Right.
Because of famous Kaplansky problem.
Correct. In fact, we did some computations with Valery and also with Mohammad Ilham Dadi, and we found that we believe that we believe that if you take a semi-Latin Quandle, then you can actually have some analog, something like Polanski's conjecture. You can claim something like that, but we don't know how to prove it. So, yeah. So you need to impose some condition. You need to impose some condition on the Quandle actually, in this case.
Other questions? Okay, so let's thank Professor Singh once more.
Thank you very much.
Thank you. And the next lecture again in 5 minutes. So see you again.